ler, né? Então, boa tarde. É um enorme prazer dar início à série de colóquios no Instituto de Física em 2021. Nós deveríamos ter começado antes, mas nunca é tarde. Algumas das pessoas na organização tiveram alguns problemas. A gente, nessa situação de pandemia, entende esses problemas de todos, e essa é uma atividade organizada pela Comissão de Pesquisa do Instituto de Física. Então, dois outros membros da Comissão de Pesquisa, o professor Oscar Éboli e eu mesmo, Paulo Nussensweig, assumimos aqui para garantir a promoção desse ambiente acadêmico tão importante para todos nós. É um enorme prazer começar a série com o professor Julio Larrea, que é professor no Departamento de Física Experimental do Instituto de Física. O Julio fez o doutorado dele no Centro Brasileiro de Pesquisas Físicas, o CBPF. Ele passou um período na École Polytechnique Fédérale de Lausanne, na Suíça, assim como no grupo de estado sólido, eu falo francês, mas eu não falo alemão, da Technische Universität Wien, em Viena, na Áustria, e mais 2 anos como pesquisador visitante no CBPF entre 2015 e 2017. Ele é docente do Instituto de Física desde 2018, ele é coordenador de um auxílio jovem pesquisador da FAPESP, e, juntamente com a professora Valentina Martelli, que é coordenadora de outro auxílio jovem pesquisador da FAPESP, estão iniciando um novo grupo de pesquisa no nosso instituto, esse laboratório para matéria quântica sob condições extremas, e o Julio vai contar para a gente hoje sobre um trabalho de uma transição de fase quântica recentemente observada e publicada na revista Nature. Então, Julio, é um enorme prazer receber você. Muito obrigado.
Ok. Obrigado, Paulo, pela apresentação. E agora vou mudar para o inglês, porque tenho alguns convidados aqui. I have to switch to English now. And thanks, Paulo, for the introduction. Also, I would like to thank the organizer of the colloquium to give me the opportunity to speak about one of the subjects that I'm currently developing here in the Institute of Physics of the University of São Paulo. And before starting with my talk, I would like actually also to thank the contributor for the recent Nature paper, in particular, Professor Henry Rono from the Laboratory for Quantum Magnetism at EPFL, and colleagues that were working intensively with me, Bruce Norman and Ellen Fogg, and also a theoretician that has a very active interaction during this time, particular Professor Miller and Professor Philip Corbel from the University of Amsterdam. What I like to actually, before starting to speak about the result in this system of strong copper, where I would like first to introduce the concept of quantum phase transition, but in a way that can be a smoothly introduction, starting from a classical, comparison and up to the quantum phase transition concept. And afterwards, what I wanted actually to bring to the audience is how the study of this system, the frustrated antiferromagnet, strong copper write, could be a good platform to study the physics of the quantum phase transition, in particular with experiments under extreme conditions using the physical property calling specific heat, right? In this moment, actually, what I want also to address is that the way how we are measuring is let's say, a kind of home-built, experimental approach, which actually allows to make a very high precision specific heat measurement under multiple extreme conditions. And that's a multiple extreme condition actually will end up with the result of the work that combining simultaneous extreme condition of temperature very close to zero and high pressure and also intensive magnetic field, all together, we will try to unveil the quantum phase transition in a Strontium-Koppel variety. And actually, at the end, I will try to finish with my conclusion of this talk. So when we just referring to a phase transition, the first things that comes to our mind, perhaps is the common, boiling of the water, yes, that goes from basically a liquid into a steam. And what we have observed in everyone, of course, is the coexistence of these two phases, right? But physics is going beyond just the simple observation and trying to explain. Perhaps at the beginning of this history, we have to mention the work done by the Charles Cagnard de la Tour, yes, almost 200 years ago, in which actually he described it by an experiment that this coexistence of the liquid and gas, yes, start from a triple point. And basically what is done is that in the variating the temperature and the pressure, you can actually see that this coexistence of phase terminates at, that he called it critical point, the critical point of water. And something that is characteristic about this coexistence of the phases is that here you describe, yes, the change of the phases by the abrupt change of the density of the particles from liquid to gas or gas to liquid. But when they reach the critical point, the system becomes actually with a continuous simply transition, and you cannot distinguish this jump in the density. And then you end up only to one single state, physical state. And this actually defines the supercritical regime where the liquid actually have a high viscosity, right? But then what you can say, this is only just a phase diagram of the water, but the phase diagram then becomes very well, let's say, investigating another system, in particular, some systems that are magnetic with a so-called ferromagnetic state. Perhaps most of you, yes, has an idea of what is a ferromagnet when you just trying to see your hard disks, that has a certain magnetism. But for physicists, what is very interesting is to understand what's happened with in a transition when the system is a kind of a magnetic disorder, right? And we call it this state paramagnetic. And by reducing the temperature, you can cross from simply a magnetic disorder state to another state in which here all the spins are aligned parallel, and you can describe it as in a ferromagnetic state. What you can see here, just schematically represented, is that for the reason that you have simply a breaking of the symmetry, the rotational symmetry from the disorder to the ordered phase, there is an effect on this. And basically, this is actually where addresses in a complete theory, yes, of the phase transition, driving by temperature, actually bringing by the Landau-Ginzburg-Wilson paradigm, okay? This is the complete theory that describes and well, sorry, and let us understand quite well, yes, the underlying physics in this phase transition driving by temperature. In particular, for this case of the magnetic system, when you cross, yes, from the disorder to the ordered phase, yeah, the separation of these phases is accompanied by the critical point, but this, in this case, this critical point has just a continuous, yes, form of the phase transition, which shows actually very interesting physics, because all the measurement that you can do or observe here close to this continuous critical point, right, simply shows physical properties quite different from the ferromagnetic or from the ordered phase and from the disordered phase. And this kind of behavior of the physical properties tell us that you have a new definition of the calling a critical behavior or criticality, right? Another point, beside also the breaking of the symmetry coming from this driving temperature phase transition, is that you can define also an order parameter that describes basically the order phase, yes, of your system. So, but the case of the quantum phase transition, yes, is basically defining as a transition and it's not driving by temperature because this occurs at temperature equals 0. separated into different phases, right? And the case here is more complex because since you don't have a theory to explain that, then you have to construct actually all the hypotheses claiming in quantum mechanics. For instance, I will bring just here an example to show how a quantum phase transition could emerge. Imagine that you have a chain of spins, right, described by this Hamiltonian. Basically, in the second term, you have the coupling between next near neighbors of Hamiltonian, yes, of the spins here represented by this energy, that is the coupling between the spins in different sides. And another term, the first one, that actually include a term associated to another coupling constant that is what is done is basically to change somehow the correlation between the spins, yes, acting in one preferential direction, in this case, along the x direction. But what is important here is that, in principle, some concept of phase transition can be even, let's say, try to represent it. For instance, if you flip the spin up to down in different sides, yes, you could end up from a magnetic state, which means magnetization 0, to another state with magnetization 0. So in this case, somehow you can still represent a time reversal symmetry, yes, involved in this type of simply change of from a magnetic order to non-magnetic order. However, the problem is more complex because since you have a quantum system, you have to see how evolves the eigenstate or the solution of this Hamiltonian. And in fact, solving this Hamiltonian, diagonalizing this Hamiltonian, what you obtain is basically that the ground state, yes, the physical state at 0 temperature, is formed either by the product of a spin up, yes, giving a magnetization positive, or a product of a spin down, giving a magnetization negative. But if you continue, if you now apply more of this, for instance, increasing the coupling constant, right? That would be in case of magnetic field, for instance, what you are doing is to actually change the type of the symmetry or the topology of this, let's say, eigenstate space, given to a magnetization equals 0 by a combination of state of a spin up and a spin down, yes? And the situation that you observed immediately that at 0 temperature, actually, you pass from one order phase to a quantum disordered phase, crossing a quantum phase transition at some critical value, right? In order to know if this transition is continuous or discontinuous, you go to a deeper, yes, let's say, investigation of this Hamiltonian. And what you observe is that the transition, in fact, is continuous. And when the phase transition at 0 temperature is continuous, is called a quantum critical point. Yes, and this quantum critical point is basically characterized by the divergence of the correlation lengths when the system approaches to the quantum critical point. So in this case, the system given by simply a spin model tell us that the transition is a continuous transition and the correlation lengths diverge, showing a quantum critical behavior. And it's not only idealization from theory, but also it can be found also in experiment that this kind of quantum phase transition exists, in particular for a system realizes in this experiment in lithium chromium fluoride. You can see, for instance, that this system is ferromagnetic. It means it's going from a paramagnetic state to a ferromagnetic state at around a Curie temperature 1.5, right? With the application of magnetic field, you change the correlations. And what you are doing is that you follow a line, a thermal line, where basically all the physics is explained by the classical Landon-Ginzburg-Landau theory. But as long as you started to decrease the Curie temperature, what you are doing is to suppress the transition continuously, right? And this continuous suppression of the transition defines the quantum critical point. And the quantum critical behavior appear even at finite temperature. In principle, if you, for instance, try to measure a magnetic susceptibility, yes, very in the vicinity of this quantum critical point, you will see the quantum critical behavior showing as a power law over a large range of temperature. different from the other part of the phases. So what we learned then from this system is that collective behavior, yes, emerge when you approach it to the quantum phase transition in the spin degrees of freedom. Instead as well, we can say that this phase transition, yes, that happen at zero temperature, and for this spin, since it seems to be continuous for this particular case of the quantizing model, just showing a quantum critical behavior. And interesting is that just by the observation, you actually can say that the system is driving to a quantum phase transition by the application of intensive magnetic field. It means you are using a not thermal control parameter. So another example that I wanted to show you to see actually the features of the quantum phase transition is what is called a system of the Mod Insulator, right? And different from the previous example, in a Mod Insulator, you actually evokes the charge degrees of freedom, electrons, right? And the interaction, the strong Coulomb interaction in the electrons, competing with how electrons are arranged in the electronic band, actually will determine the ground state of insulator of a metal, right? Here is an example in the two-dimensional system, Mod Insulator, right? Where basically show a phase, typical phase diagram of Mod Insulator, where either, yes, you can tune simply the Mod Insulator, but put in electrons, and of course, change the interaction, the Coulomb interaction, in this direction, in the horizontal direction. Then you can cruise from metal to Mod Insulator or metal. Or if you can stay here from one point of inside the Mod Insulator phase, what you expect that is that, for instance, at the beginning, you can have simply a gap opening in the conduction band, yes, but by the application of pressure in this direction, you started to narrow this conduction band and close the gap, inducing a metallic phase. So therefore, by the application of pressure and closing the gap of the Mod Insulator, you pass from a Mod Insulator phase, in principle, to a metallic phase. But this is not only a theoretical prediction. In fact, what one can observe is that in a synthesized material, yes, it is a molecular material that shows this 2D Mod Insulator state. What you observe is that, first of all, you can pass even at almost a very low temperature, defining a quantum phase transition from a Mod Insulator to a metal, right? But if you just follow and increase and take the measurement in many of the temperature, what you are seeing is a sharp transition defining a first order transition that terminates at the critical point here for the Mod Insulator. So in this case, trying to see, yes, the correlation in the electron degrees of freedoms, what you are seeing is that for the case of the Mod Insulator, apparently the transition, the quantum phase transition, is discontinuous, right? There is a jump between the charge carriers with density from the Mod Insulator to the metal state, of course. And in particular for this type of system, to achieve the quantum phase transition, you need actually the application of high pressure. Another time, a non-thermal control parameter, right? So just then, to try to summarize this first part of my talk, yes, to actually distinguish a classical from a quantum phase transition. Basically, in a classical phase transition, what you are doing is a change of the state driven by the thermal control parameter, while in the quantum counterpart, you have a change of the state driven by no thermal control parameter like pressure or magnetic field. The second point that we can see also that here in the classical phase transition, we have a theory, yes, the Landau-Kismus theory can actually predict all the critical behavior, while in the quantum phase transition, still there is open questions to understand what is the underlying physics emerging in this zero temperature phase transition. So, but what is interesting is that beside the exciting, let's say, basic knowledge that the quantum phase transition can bring us is that there is interesting correlated phenomena that can emerge from the quantum phase transition, as we see, like entanglement of spins, or either and other phenomena like superconductivity in the case of electron degrees of freedoms. Okay, now actually introducing now the concept of quantum phase transition, I wanted just to speak about the compound, the strontium-copper boride. And this is actually the strontium-copper boride, that is the realization of the famous Shastry-Sutherland model, right? And to explain this kind of model, actually, you have the material that is a tetragonal crystal structure. We have see here in this panel, yes, a projection on the plane A and B direction, while if you see just perpendicular to this plane, you will have the C direction that is showing here in the lower panel, right? So basically you have layer peeling up or peeling down along the C direction. What you observe here is that the spin and a half is like on the copper sides, right? Formed just a singlet of dimer orthogonal one to each other. Therefore, you can see that there is a degree of magnetic frustration because it's in this singlet here that is actually characterized by the intradimer coupling J. Yes, have simply a singlet state. It means you have an antiferromagnetic coupling or antiparallel coupling. And if you put in another, using the orthogonal singlet, the first one in the next near neighbor, what you will see is that for one point, you can still have, yes, the antiferromagnetic coupling. However, for the other one, not. And therefore, you will create instability in this stabilization of this, let's say, spin orientation. And this kind of instability brings what we call it quantum fluctuation, or simply effect of the magnetic fluctuation. And therefore, what important things about the coupling inside the plane or along the planes, yes, is that the system, for instance, show a more interesting, coupling between the spins, because you can have here the intradimer J over, yes, the next near neighbors, or the interdimer coupling J prime, that somehow is not negligible, right, the ratio. However, for the other case, you have that the coupling between the layers along the C direction is very negligible. And therefore, the system can be considered uniquely as simply a bidimensional system. And therefore, here the Shastry-Sutherland model can be very well addressed to this system, and is, of course, very well seen by theoreticians in the way that they can diagonalize it exact and give the exact solution of this Hamiltonian. And the exact solution of this Hamiltonian brings a different base of, eigenstates related to the spin, where the ground state is a singlet state, yes, with a spin somehow in the dimer state, antiparallel, characterized by energy of gap that separate the spin singlet state with the total spin 0 to the excited state with the spin total spin equal 1. And this gap is determined actually by theory in the order of 30 Kelvin, and also confirmed by experiment to be in this order. So another interesting point is that if you just see the possible different order that can be arise from the simple change of the ratio, actually theoretician also made the prediction that, for instance, you can obtain different phases. In particular, here I show a more general phase diagram, right, for this dimer model, and strontium-copper boride according to the ratio, yes, of the J prime over J can be placed here by, if you change the ratio, for instance, by application of pressure or magnetic field, what you can do is to tune, yes, the system from this dimer singlet phase to a simply placket phase. In this case, the placket phase will contains now an entanglement of 4 nearest neighbors dimers, right? Or if you continues to be even increasing this pressure or magnetic field, what you will do is just to pass to another phase, in this case, quantum antiferromagnetic order. So this is a very interesting phase diagram with promising to inspect different order passing to a different zero temperature quantum phase transitions. And among different experiments that have been done and also theoretical predictions, the most maybe suitable for this talk is to present the inelastic neutron scattering experiment under high pressure. Yes, some years ago published by a group when I was still in Lausanne. And what we have been reported is that basically neutron scattering is very sensitive, of course, to a magnetic excitation. In this sense, they can simply measure this gap, yes, that separate this singlet state from the triplet state, okay? And with the application of pressure, what you are seeing here is that pressure actually tuned to lower energies, the gap, right? And at a pressure close to 21 kilowatt, what we have seen is that in addition to this excitation of the gap, appear another excitation at much lower energy. And then with the help of theoretician, we explain this new energy scale at lower values as a signature of the placket phase. This was the first experimental evidence of the existence of this entanglement of dimmer states. So just to summarize, in this part of this result is the pressure, temperature or energy phase diagram, just with pressure. And what you can see is that pressure actually tuned to a decreasing of the gap of this singlet to the triplet state. A second energy scale at lower temperature or energy appear associated to the existence of the placket phase, and it's expected that at high mass pressure, this placket phase evolves in antiferromagnetic quantum order. But until this time, we haven't actually understood what will happen in the phase transition between the dimmer and the placket phase. So therefore, this time of this publication was still an open issue to clarify. And then this is what is coming suitable, our experiment of a specific heat under extreme condition, right, in this system. Here I have shown just a simple view of how, for instance, the crystal are growing. Yes, in principle, a big single crystal provided actually by collaborators at the Pictorial Institute. Yes, in this case, the crystal is growing along the Z direction, right? For our experiment, actually, it's growing in a peak because people are doing also neutron scattering experiment. But for our experiment under pressure, we need only just a few milligrams of this sample. Yes, we cut it on a slide and we can put it in this pressure cell, non-magnetic, right? Reach pressure up to 30 kilobar. The experiment were actually performed in the laboratory of Professor Ron at EPFL, which actually count with a dilution fridge unit immersed in a helium-4 bus that also is provided by the magnet up to 9 Tesla, right? I will give you now another details about the experiment, but something like, I have to say that at the beginning, when I arrived to work with Professor Rono, I remember that the project was to develop a specific heat measurement under high pressure, but at that time he was a tenure track professor, and basically we started the experiment from scratch, right? So therefore we have to make all the type of mounting of the experiment itself and try to even to upgrade this experiment of a specific heat under simultaneous extreme conditions. So then this is just a pictorial representation of the experiment. And what we can see here is that, for instance, our method consists in a measurement of the heat capacity of your sample, right? By applying a modulated heat on the sample and measure the difference, yes, of temperature simply of the sample by also a modulator. If you see here in the steady state equation of the system, consider that you can apply simply a modulated current, just dissipated in a resistor here, right? your signal that you will pick up would be in a double of the frequency that you apply as a heat, as a modulated heat. This is why we call it a second harmonic method, right? Just if you make the calculation, of course, you end up that the modulated temperature, yes, that you are measuring from your sample is basically related to your heat capacity. So making such kind of simple measurement of your modulated signal on the sample, you can obtain directly, yes, the heat capacity of your sample. But the situation is not really easier. Why? Because as you see, it's a modulating technique and we depend on the frequency that you apply in your heat dissipation. Therefore, just to give you an idea, if you select a frequency, yes, much higher than the frequency to select your specific heat, then what you will expect is that most of your heat so only dissipate in a small part of your sample. And therefore, your signal is quite small that any instrument can resolve. However, if you apply a very small frequency, right, the heat is dissipating more over the whole system, even touching the pressure cell, and therefore your signal will only have more contribution from the addenda and from the pressure cell that you will not see the signal of the specific heat. Therefore, a compromise between two different limit of frequency, yes, will actually set the good criterion to obtain the specific heat of your sample. So in this case, we try to approach the measurement of the heat capacity from the different perspective. Instead to put the sample on a calorimeter, we put the calorimeter on the sample. This is what we call it, just we give the baptisms, lap on the slab. And that is consistent in basically a sputter, a heater. This is a thin film of 20 nanometer, a platinum film on the sample. Here on the other side, we are trying just to measure the modulating temperature that would be related to the specific heat by simply, for instance, a signal in a double harmonic with locking. Of course, the thermal link that you have, yes, of your sample with the surrounding, considering that also this sample is immersed in a pressure medium and in the pressure cell, yes, is also important because according to how stable is your temperature, you also will end up to a different influence in your heat state equation. And in addition here, this is just the backside of picture of this mountain. Yeah, this is a sample holder for our pressure cell. And in this side, I represented here a LED, yes, that is working like a manometer. We measure here the superconducting transition, yes, and the pressure, our calibration is ex situ. It means every time that we change the pressure, we have to remove the cell, warming up, and then change the pressure and put it again. Another point that is very interesting here is that here actually I represented the pressure cell, but you coupling thermally to the cold finger of the dilution fridge by simply different pieces made of copper, right? And everyone knows that works basically with magnetism that when you apply magnetic field, you produce eddy current. And this eddy current can disturb your experiment. So therefore we have another issue to sort it out. And this is what we actually managed to do, yes, to just diminish actually the influence of the eddy current in our experiment. So now I wanted to show the results. And what we have seen here, is that first of all, how reliable are our measurements, yes? So what I was showing before is that the experiment here is following this model. We have to change the frequency, yes? And we do that in a different, actually, temperatures, right? Isothermal curves. And just to give an idea, each point that you are seeing here takes around 3 or 4 hours, right, of measurement, depending on which frequency you are. So basically, a curve could take at least a day, yes, or sometimes even lower, depending on the frequency. But overall, this, for instance, cure of the specific heat is obtained by fitting, yes, the frequency scan of the modulated signal. Then you obtain here for each cure a point of the specific heat and plotted against the temperature, right? So this measurement, for instance, takes around 3 weeks just to determine precisely the specific heat of the sample. And how we know the accuracy of our measurement? Well, first, we try actually to compare a measurement of our sample with our method, doing first the measurement inside the pressure cell that we call in here in, is the blue curve, right? And after we take the same sample and measure it out of the pressure cell at ambient pressure, right? And we see a good coincidence simply between these two configurations. It means that our method actually simply goes exactly to the sample and not to the surrounding or the addenda contribution. We remove this addenda contribution influence. On the other hand, if we compare with a reference in a measurement of more in adiabatic or simply a condition that type this time relaxation technique, what we have seen is that our measurement coincides very well. It's in a well agreement, giving us actually the confidence of the accuracy of our measurement to resolve a specific heat absolute value in an order of 5%. Yes, knowing that our measurement has a very reliable data, yes, we can also proceed to calculate, for instance, the energy cap associated to this shape of PAM of the specific heat in the order of 30 Kelvin, and also the different parameter or chain coupling constant related to the dimmer singlet state. Yes, the way that actually theoretician helps to calculate this kind of cap and other parameters doing the exact analysis by numerical calculation. But something that is very interesting and also not worth it to say is that when we are applying pressure, yes, basically what we have seen is that our frequency where maximizes the specific heat would change, right? For instance, here I'm plotting the time relaxation that is somehow inverse proportional to this frequency where you obtain the specific heat. You can see that this frequency changes with the pressure, right? And this is a very good, let's say, criterion to consider, because in principle, what people have been done or using the specific heat and the pressure, normally what they are doing is just to take the modulating temperature, right? To take the inverse and relate it to the specific heat. But this is not our case. What we did is actually that for each pressure that we set, we are doing in all this time a frequency scan. And with that, we have avoided that the specific heat simply could max by a frequency dependence, just to maximize the specific heat. So in this sense, our measurement has this high accuracy, yes, in determination of the heat capacity. And in addition, we observed that simple this kind of the frequency dependence to maximize the specific heat somehow becomes negligible when we measure the specific heat for pressure above 18 kilobar. So above the 15 kilobar, then we can, in principle, take this kind of criterion, taking just the frequency to maximize here the specific heat, and then related to the specific heat. So another interesting point is that we make the measurement in a different batch of samples to get, you know, the to be sure about the reproducibility of our results. And what we have seen here, for instance, in this right upper panel, is that putting a different modulated thermometer, yes, in the different places, first of all, you obtain the same result, right? And we tell us that we don't have a gradient of the temperature across the sample. And in addition, that the specific heat that we are taking simply is taken from all the sample. In addition, when we apply the pressure, yes, and doing our measurement of the frequency scan, what we can resolve is a very sharp peak, right, obtaining in the specific heat. And if we try to select the frequency when the specific heat maximizes, yes, then we fix the frequency and then we make a temperature scan. And this is, the comparison is very well, yes, in agreement with our analysis and more longer time of measurement. So therefore, in this condition, actually, what we can do is to take the frequency fixed and make a temperature scan above 18 kilobar. Now I will present the result of the experiment under high pressure, right? At the beginning, we can distinguish two different regimes and different features in the specific heat. The first one, as I mentioned before, is the gapped single state dimmer phase, where you have this hum, right? And here, when you apply pressure, this pump started to decrease till more or less 16.5 kilobar, but at 80 kilobar appear simply a chart in the specific heat. Okay, this tells us that there is something very different from the simply decreasing of the spin gap, just related to the separation of the cyclic and triplet state. So another thing that you can see is that basically, also here, you can see in the 20 kilowatt appear the chart peak. Another thing that you can observe is that at lower temperature, you can distinguish another anomaly that will be related then and another type of order or phase. And here, what you can observe is that at 80 kilobar, this small anomaly becomes stronger, right, in 20 kilobar. And after, when you started just to increase more the pressure, the chart peak started to get broadened again and go into the high temperature, right? Here till 26.5 kilobar, that is the limit of our pressure in this experiment. And after, with a small peak, what you see here is that the chart, this small peak started to decrease, but keeps almost at the same temperature, right? So the observation is saying that we have at least two different phases, and something completely happened, yes, in between 18 and 20 kilobar that tell us that could be maybe a quantum phase transition. In order to infer more about the physics, yes, in this problem, we apply also magnetic field and the combining effect of pressure. We take this chart peak at 18 kilobar and started to apply magnetic field, yes. And what you observe just from the experiment is that by application of magnetic field, this chart peak started to decrease, yes. The position at temperature for each field are plotted here in this curve, right? For 18, 2 kilobar is this turquoise color here, right? And the same also for the other pressure that you can see is decreasing in this way, right? And for the small anomaly, what you observe is very completely strange trend, because for 18.2 kilobar, for instance, this small anomaly with application of magnetic field is decreasing until to be suppressed completely. And this temperature we are plotting here, suppressing almost at 6.5 Tesla. And after, what we are doing is in higher pressure, we again see that the magnetic field for this small anomaly also decrease, but not suppressed. Instead of that, increase again, right? And it becomes more noticeable at the highest pressure that only increase. And this is here plotted. Therefore, all this data combining by the observation itself, by the experiment, and their simultaneous effect of pressure and field tell us that exists a quantum phase transition between 18 and 20 kilobar. But we don't have interpretation till we have the help of theoreticians. And theory actually brings just a calculation, advanced calculation, yes, based on the infinite projected entangled per state models, right, that basically calculate the eigenstate state at finite temperature, yes, and what we can see is that theory managed actually to reproduce the chart peak by simply considering increasing of the density of population of the triplet state. And after, of course, passing through simply an enhancement of this ratio of the dimmer of the exchange coupling, you again reproduce the decreasing of the chart peak, like also the experiment shows. if you just see another consequence of this theoretical calculation is the first one is that our experimental phase diagram here is a color map representation. If you see, we are plotting the pressure, yes, or the intensity of the heat capacity over the temperature as a function of pressure, where here the most intense, I mean the peaks, yes, in the specific heat are here at the quantum phase transition. And the theory also managed to reproduce the same type of quantum phase transition, given this sharp peak on the intensity of the heat capacity, right? At the ratio between these couplings in the dimmer arrangement, 0.68. This is a very important value because in many calculations, we can see also, for instance, another feature of a discontinuous phase transition, in particular because here you have an enhancement of the correlation length. Here is another color map that shows that the correlation length becomes bigger, yes, here at the quantum phase transition, yes, in a long line that terminates in a let's say, finite temperature, yes, and therefore this finite temperature, just comparing our all type of color map phase diagram, we conclude that we have a finite temperature critical point. And another characteristics of this finite temperature critical point actually comes also for the discontinuity of the correlation function of the spins that, as you see here, becomes very discontinuous, right, at the quantum phase transition and terminate at the critical point. And another evidence of this discontinuity, and given is by the simply scaling, yes, as long as you start here reaching the discontinuity, that tell us also the existence of a universality of first order transition classified in a two-dimensional Ising exponent, 1/8. So in this case, combining experiment and theory, numerical calculation theory, actually we can conclude that this quantum phase transition terminates at a finite temperature critical point, right, in which correlation lengths enhance, and you have also a discontinuity in the function of the spin-spin correlation. So then to summarize here, our experimental result in this Strontium-copper boride, we have the combined effect of temperature, pressure at magnetic field, and we managed actually to define a three-dimensional phase diagram. A quantum phase transition actually set in this system, yes, with the coexistence of a placket phase and dimmer phase, and this quantum phase transition terminates at a critical point at the finite temperature. And in particular here, the placket phase under magnetic field shows a much richer physics because, as you see here, the placket phase under magnetic field evolves and simply changes to antiferromagnetic phase, okay, and bringing a new type of quantum order in this system. So let me just now to conclude these results. And we can actually see in here similar critical physics between classical physics in water and Strontium-copper boride. We can say that they can share a critical behavior only by the termination of the first order phase transition in a critical point. However, for the case of a Strontium-copper boride, the physics is much richer, right? Because here, first of all, you have an entanglement of different spin states in a placket state. And with application of the magnetic field, even you can induce another type of order, right? So then what we can say is also that the Strontium-copper boride is one of the most exciting quantum spin systems ever synthesized, and still continues to offer, open, let's say, physics, in particular to investigate the emergent correlating quantum states, right? And if in some direction that also you can imagine for somehow an avenue for application or realization of functional materials. In addition, we have seen that this first order phase transition, yes, that becomes discontinuous also shows a very interesting physics, because some states emerge close to this discontinuous phase transition. And of course, our experiment shows that we need extreme conditions to unveil this quantum phase transition. So just before finish my talk, I would like just to present very quickly our future plans to be developed in our recent lab, LQMed. And in particular, we wonder actually to continue to investigate the phase diagram of Strontium copper boride. Yes, as I mentioned before, in the placket phase, we have by magnetic field, yes, an induction of antiferromagnetic phase. However, we still don't know which kind of type of phase or type of quantum phase transition is, let's say, tuned. And therefore, a new experiment in the critical region, yes, around the critical point, is planned to be performed, and also in a high pressure, because we expected that this placket phase evolves perhaps in the interferomagnetic phase, or possibly in another emerging quantum phenomena like superconductivity, right? And for that, we will continue to collaborate with Professor Bruno from EPFL, and involve also a student under my supervision. In addition, what we have seen here is just a problem with the quantum phase transition involving spin degrees of freedom, but the physics even can be more complex in case that you add the electron degrees of freedoms, like for instance in a system like it's a heavy fermion, this heavy fermion cerium-3, palladium-20, silicon-6, and offering another type also of degrees of freedom, that is the orbital degrees of freedom, right? So this previous measurement under magnetic field in this heavy fermion showed that by the application of the magnetic field, you disentangle, yes, each of these degrees of freedom in two different quantum critical points. However, by understanding, or for that understanding of theoretician, we need a kind of parameter that actually tune the hybridization. And this is just a kind of role of the pressure, right? That could in principle mimic this tuning of the hybridization. Therefore, experiment at the high pressure in this system becomes even more interesting. And in order to get progress in this kind of research for this particular compound, we're still having collaboration with Professor Passion from the TU Wien, an exchange of know-how in high pressure experiment with Professor Giovanni from Johannesburg, and also involve people from our home institute and a student under my supervision. So something that I also wanted to share with you is that in addition to the not canonical or not tuning, not thermal control parameter, also we can do something else, right? As a tuning control parameter. This is a very interesting idea to tune a quantum phase transition by another non-canonical tuning control parameter that would be, for instance, the reduction of dimensionality from 3D to a 2D, managed to, for instance, synthesize thin films, or from about 3D to reducing the size of the system, producing nanoparticles. In both cases, in principle, we can mimic the effect of some, effect of pressure. And we actually selected one system, that is the iron gallium 3, doping with germanium, which in particular in this previous investigation, what we have seen is that the system, by simply substituting gallium by germanium, you induce a non-magnetic state to a magnetic state, right? Passing possibly, or likely, to a quantum critical point, that this is still an open question. But the way that we are trying to approach this kind of investigation by using a non-canonical tuning control parameter will give us a more, let's say, a straightforward evidence of how the quantum critical behavior actually appear, yes, in a more reduced atomic scale. A good news is that we managed to synthesize actually a sample of iron gallium 3 in a very well, let's say, characterization of single phase. Of course, the characterization and the physical property measurement involves different collaborators from our home institute and also for another multi-user labs where basically we'll provide access to experiments like muons or neutrons and also a high pressure experiment in synchrotron radiation, and also involves some student under my supervision. And just also I would like to show how now with our lab, yes, we have just been certainly recently some equipment that allows to perform experiment down to 9 Kelvin and also setting a high pressure experiment. Yes, we're using a cryo-free duplex, right? And also our lab is equipped with some instruments to just manipulate the sample inside the pressure cell. Here, actually, I show a photo of a home-built pressure cell constructed in the workshop of our Institute of Physics. Yes, and we are here in a process of testing. And of course, this lab has the collaboration with Professor Martelli, that is also a fellow of the Max Planck FAPESP, right? But despite that, maybe the facilities is not complete enough to combine it with magnetic field of very low temperature. However, the future is much promising because we are planning in a very near future to set a new instrument, a cryo-free cryostat that will allow, in principle, to reach temperature much lower to 1.5 Kelvin, in addition to apply magnetic field up to 9 Tesla, and to, say, set a versatile experiment under high pressure, right? This is a customized, actually, cryostat, will allows, in principle, not only install new future experiments, customized, but also the possibility to eventually in future set a dilution-free setup, yes, that will allow us to reach temperature much closer to zero value. So, and finally, let me just acknowledge the student that are under my supervision that still has a very high motivation to continue even in this time of COVID, right? And I will finally thanks also our funds agency in Sao Paulo, FAPESP, to give us the support actually to mount this lab and also for all formation of this student. And thank you very much, all of you, for your attention.
Oh, thank you, Julio. Now I actually don't know if I should moderate in English or in Portuguese. Let's make it in English because I guess everybody can follow. So we are open for questions. Anybody, please either open the mic or just raise your hand.
Julio?
Yeah.
I have one question is about the near and long-term future. How long do you think that is the lab operational nowadays, or you still need to complete things, and when it's going to be operational in São Paulo, to do the experiment in São Paulo?
Yeah, it's a very good question. Okay, thanks for the question. Actually, it's very timely. Basically, the most maybe important part for our experiment is to access, of course, to very low temperature, right? And some of this system, I don't know, maybe I can show you, yes, in particular, some system like the Strontium-Copper boride partially, and this system, for instance, doesn't need too much low temperature when I say not in the millikelvin regime. And so we are almost close to, say, close the contract to acquire this cryo-free system with the support, of course, of the Institute of Physics, right? And also department and FAPESP, and also, you know, combining fellows and grants with Professor Martelli and myself. And the customized cryostat takes around 8 months. I would say that according to what we have at the moment with the COVID and on all these problems that you know here currently have, I think it's I expect optimistically in almost 1 year, we will have all the facilities to really, you know, launch our experiment under simultaneous extreme conditions. Yes.
Marcia, I don't know which Marcia wants to ask a question. Please open your microphone.
Hi, Julio.
Hi, Marcia. Hi.
Hi. Very nice, your work. I would like to know that, I know that you prepare your own samples.
Yes.
It's difficult to prepare samples with the properties that you want, né? In terms of structure, etc. What are the problems in the preparation of your samples? Do you have it?
Yes, actually, you brings a very interesting question. I didn't say, of course, you said because the limit of time always you have to run. But here, actually, the effect of atomic disorder that sometimes for some particular investigation, you know, you don't consider here is very dramatic. In particular, a quantum phase transition itself becomes completely obscure or misleading when you have certain impurities in the sample. So therefore, I would say that for the case of this Strontium-Copper boride, you know, I have at least a good collaboration with the people in Switzerland that provide the sample. For the case of Cerium Palladium 20 as well, with people in Vienna. But now we are trying here in USP to create our own, you know, know-how to at least produce samples that has not this kind of impurities or simply spurious phases, right? It deserves, you know, a very wide, perhaps a number of experiments in the microstructure, in many details. This is why we have to combine different, techniques, right, in multi-user labs to let us know actually that the sample is a very good quality, right? And just the question, the answer to the question is that disorder in this system dramatically affect the physics of the quantum phase transition. It has to be very good, high quality samples in general.
So you are developing ways to prepare your own samples here.
Exactly, yes. This is actually particularly this sample, the iron gallium germanium. That also you are offering me a lot of help in, in the access to the lab.
Curiosity. Thank you very much and congratulations for your work.
Thank you.
Thank you, Marcel. Oscar, you had a question from YouTube.
Yes, it's from Rivers. He says, thanks for the interesting talk. Do you have any intuitive way in which we can understand that this phase transition should be first order rather than continuous?
I'm sorry, you have any?
Intuitive way.
Intuitive, okay, intuitive way. Yes, actually what we have seen here is the first things is the absence of critical behavior, yes, in the specific heat, right? It's more than intuitive, it's an experimental observation. Normally what you're expecting for instance, continuous phase transition is the signature is the critical behavior, the quantum critical behavior. And then you just stop, for instance, in the pressures around 18 and 20 and makes different, physical property measurement. We haven't seen a critical behavior. And the accent actually said also is one indication of the absence of continuous phase transition. And of course, the other intuitives come from the theoretician that they try to also simulate a continuous phase transition in the scenario, yes, but it didn't work out, and therefore experiment and theory actually can, in principle, match very well.
I'd like to, you mentioned in the slide you show a discontinuity in the dimer spin-spin correlation function, and you mentioned entanglement as one of the characteristics of this phase transition, right? Can you elaborate a little more on that? Can you tell us a little bit more about whether you can control entanglement in this system?
Yes, it's a very interesting question. I think it's still an open question in the sense that we have still seen, exploring in this diagram, phase diagram with magnetic field, right? Because something like we normally can attribute to this critical point is that a finite temperature, yes, it's not only a zero temperature, you have this entanglement of states, right? But the point here is how this entanglement could become more and more dense, or even more robots, as you maybe wanted to know. And therefore, still we need to make more experiments in order to just, systematically tailoring this kind of entanglement of the state according to how close are to the phase transition, being continuous or discontinuous.
Just a little follow-up. I'm not sure I understood very well whether you're directly measuring correlations. How do you have experimental access to this, or is this just the comparison of theory and data? You're not directly extracting this from the data, are you?
Indeed. Actually, this is a very untimely question, because something like still is pending to do, of course, is how this correlation can map it. Yes. For instance, one thing would be to this correlation, the spin-spin correlation, be in contact with a phonon bath. Yes, where you actually determine what you can, just how this correlation changed your phonon bath in case that is having some trend. Yes, and but we still don't know exactly the answer for this question. Yes, yeah. But this is a future experiment for sure that we have in mind to actually idealize one experiment that measure more directly this spin-spin correlation. Yes.
Hello, Julio.
Hi, Marcelo.
Hi, thanks for your talk. It was really nice, and got curious because you could go from could map the transition from the dimer phase into the plaquette phase, sure. And from theory, you expect to see some structure beyond that of 4 spins coupled, or say a sort of 8 connections, or it will go right into that antiferromagnet. There should be some tail appearing at the end of that plaquette phase.
Yes, right. You actually tell us about how the plaquette phase, you mean, evolves before going to the antiferromagnetic phase, is what your question means? more or less?
Yes, because you go from dimer to the plaquette, and
Yes.
beyond that, you could get a higher order coupling of spins before solving it.
Yes, actually, what we have in this context is that, sorry, when you are induced in the plaquette phase, yes, you have still the singlet dimer taking in, you know, 4 different, let's say, point of the dimers, but this kind of plaquette phase, the bonds, right, evolves in a way that simply with a particular ratio value, yes, your basically triplet states in this particular also a critical ratio of the plaquette to antiferromagnet state simply decrease. Yes, again this triplet, and then you have again this possibility to have simply a translational, yes, order, and the way that you have the common antiferromagnetic coupling. And actually theory modeling that, yes, by simply trying to make the different products of the dimmer till they find, of course, the critical value of this ratio, yes, of in this ratio that define the bonds, this intradimmer and interdimmer that was explaining in this picture actually here, right? According to that, you have different configurations, but of course, always depending on this coupling of the radio. And this is why they are predicting theoretically with a normal, let's say, advanced numerical calculation. Of course, in our measurement itself, we are seeing simply a different anomaly in the specific heat. Yes, and therefore, the way how we compare is just by, let's say, a guide from theory that this is associated to the, you know, a different phase.
Thank you very much.
Julio, we have another question from YouTube, from Caetano Miranda, whether you can imagine other materials with similar behavior, or what makes this compound that you studied in the Nature paper so special in its atomic electronic structure. I'm sorry, I just can't say the name of the compound. It's strontium.
It's a strontium copper boride. I think your connection is bad, Paulo. It's gonna back. Hello? I think, hi, Paulo?
But so could you tell, okay, can you hear me? Can you hear me now?
Now, yes.
Okay, so if you can imagine other materials with similar behavior, or what makes it so special in its atomic electronic structure?
Well, at the moment, I cannot imagine another material, despite that there is other, let's say, close materials, similar, showing also magnetic frustration, like the lattice, yes. The KTIF also materials could be. And what is maybe makes more interesting is that this material actually show a very well localized spin, right? Even that you have electrons there. Well, the information about orbitals, bands, and so on, basically started to be simply there as a background, but it's the spin that plays the role. And I think this is maybe for our point of view, in my point of view as well, it's very interesting because you acting completely, yes, to the spin degrees of freedom, and of course, is very well modeling, you know, by theories, yes, and especially by this Shastry-Sutherland two-dimensional lattice, right? And spin square spin lattice, yes. This is what maybe becomes very special.
Thank you. My internet indeed is a little bit unstable. So if I freeze, Oscar will take over. Do we have any further questions or comments from the Zoom audience or from YouTube? Any further questions? Cauê Ribeiro, please.
Professor, thanks for your presentation. It was very interesting. Can you hear me?
Yes, I can.
I would like to ask, here in your Nature paper, you measure the heat capacity associated with the spin and the degrees of freedom of the electronic part of the Hamiltonian, the spin part are disentangled, right? And I would like to ask, how do you take only the spin contribution in your heat capacity, disentangling the electronic part, to compare with the experimental data and theoretical data?
Yes. Well, first of all, we don't have here electronic part because the spin is the electrons are really localized, right? And we don't have free electrons, but we have phonons, for instance. And here, what I didn't mention, but it's very timely also your question. Here, what I didn't mention is that basically by simply the theoretical calculation, they always will consider the phonon contribution, right? And always simply they were trying to subtract this phonon contribution in all this calculation. But of course, if you see here why, we have certain, let's say, slope when increasing the temperature because you have the phonon background there, yes. And this is something like actually simply, I didn't say, but it's a very good comment, right? But about the electronic, the electrons are quite localized, so there are no free electrons, and then you don't have this electronic contribution to take into account in this point.
All right, thanks.
You're welcome.
Thank you. Any other questions or comments? So Oscar just says nothing further on YouTube. So then in that case, I suggest we all open our microphones to thank Julio for this wonderful talk.
Thank you.
And I would like to invite you all to come back next week. Next week, we will have a talk by Professor Sergei Frolov from Pittsburgh, who will talk about the physics of Majorana fermions. And I guess you've all followed the controversy, the recent controversy with the retraction of a Nature paper that purported to have a measurement of those fermions. So we're going to hear a lot about that next week. So please come back all and be welcome. Thank you again, Julio.
Thank you. Thank you for all. Thanks. Thanks a lot. Thanks.
So we are interrupting.